Somewhere in the North Sea, roughly 200 kilometers from the nearest coastline, a vessel the length of 3 football fields holds itself perfectly still against a 4-knot current. It is not anchored. 12 azimuthing thrusters, each one capable of producing several thousand kilowatts of thrust, fire in choreographed opposition to keep the ship's position accurate to within a single meter. Below the stern, a steel pipe 30 inches in diameter descends into water so cold and dark that sunlight has never reached the bottom. The pipe does not go straight down. It curves, first bending gently away from the ship like a diver leaving a board, then sweeping back toward vertical somewhere far below, before finally flattening out along the seabed hundreds of meters beneath the surface. From the side, the shape is unmistakable. It is the letter S, drawn in steel, hanging in the dark. Why does it do that? Why not lay the pipe straight down, or at a steady angle, the way you might imagine sliding a garden hose off the back of a boat? The answer turns out to be one of the more elegant pieces of applied physics in all of civil engineering, and once you understand it, you will never look at an offshore gas field the same way again. The pipes that carry oil and gas from the seabed to processing platforms are not flexible tubes. They are rigid carbon steel cylinders, often 30 inches or more in diameter, with walls that can be over an inch thick. A single 12-meter joint of that pipe weighs roughly 2.5 tons. Laid end to end, a deep-water pipeline might stretch for hundreds of kilometers, and every meter of it has to travel from the surface of the ocean to the floor without collapsing, kinking, or exceeding the material's yield stress. Steel is strong in tension. It is far less forgiving when you bend it past its elastic limit. And bending is exactly what happens the moment that pipe leaves the back of a ship and begins its descent. Here is the physics that governs everything. When you hang a heavy chain between 2 fixed points, it naturally forms a catenary, a smooth, gravity-defined curve that distributes tension evenly along its length. A steel pipeline behaves similarly, but with a crucial difference. A chain has no resistance to bending. A steel pipe does. It has what engineers call flexural rigidity, meaning it actively resists being curved. Force it to curve too sharply and you no longer bend it, you buckle it. And a buckled pipeline, at depth, does not dent. It collapses. The external water pressure at 3,000 meters of depth is roughly 300 atmospheres, or about 4,400 pounds per square inch. A pipe that has lost its circular cross-section at that depth will be crushed inward almost instantaneously. So the pipelay engineers face 2 simultaneous constraints. The pipe must curve enough to travel from the surface to the seabed. It cannot go straight, because the seabed is not directly below the ship. But the curvature must never, at any point along the descent, exceed what the pipe's material and wall thickness can tolerate before buckling. These 2 constraints define the shape of the S, and they are managed by controlling exactly 2 variables, the tension applied to the pipe at the point where it leaves the vessel, and the angle at which it departs. On a traditional S-lay vessel, the pipe is welded together in a long horizontal production line running the length of the ship. It then passes over a curved steel ramp called the stinger, which extends from the stern into the water and controls the upper bend, what engineers call the overbend. This is the top of the S. The stinger guides the pipe away from the ship at a controlled angle and radius, preventing the pipe from bending too sharply as it first meets the water. Tensioners, essentially massive sets of rubber-tracked clamps gripping the pipe, maintain a precise backward pull, counteracting the weight of the pipe hanging below. The weight of the catenary section in between is what creates the lower bend, called the sagbend. This is the bottom of the S, where the pipe transitions from its steep descent back to nearly horizontal along the seabed. Both the overbend and the sagbend must stay within allowable strain limits. Engineers calculate these limits for every pipe specification and every water depth before the first joint is ever welded. Now here is where the common sense guess goes wrong. Most people, if they thought about this at all, would assume that more tension must be better, pull the pipe tighter, keep it straighter, stop it from bending. That instinct is almost exactly backwards. Reducing tension allows the catenary to deepen, which reduces the radius of curvature in the sagbend and risks buckling at the bottom. But increasing tension excessively makes the stinger angle steeper, which increases curvature at the overbend, and risks buckling at the top. The correct tension is a narrow target between two failure modes, one on each end of the S. The tensioners on a large S-lay vessel like the All-Sea Solitaire, which has a total tensioning capacity of roughly 1,000 tons, are not pulling hard to keep the pipe straight. They are pulling to precisely the right amount to keep both bends within tolerance simultaneously. Which of these constraints would you least want to get wrong at 3,000 meters of depth? Leave your answer below. But S-lay has a ceiling. As water depth increases, the angle at which the pipe must leave the vessel to reach the seabed gets steeper and steeper. At depths beyond roughly 1,000 meters, the stinger would have to be impossibly long to manage the overbend at a shallow departure angle, and the sagbend curvature becomes extremely difficult to control. The S begins to fail as a geometry. This is why ultra-deepwater pipeline installation requires a completely different configuration, J-lay. In J-lay, the pipe is not laid horizontally. It is assembled vertically, inside a tall tower mounted near the stern of the vessel. It leaves the ship at angles ranging from roughly 45 degrees to nearly vertical, sometimes within 10 degrees of straight down. The result is not an S. It is a J, almost vertical near the surface, curving gently as it approaches the seabed. The overbend essentially disappears. There is only one significant bend, at the bottom, where the pipe transitions to the seafloor. Because the pipe departs so steeply, the catenary length is shorter, the sagbend curvature is more controlled, and the tension required is dramatically reduced. Think of it this way. In S-lay, you are trying to lay a steel pipe across a table while holding one end. In J-lay, you are lowering it straight down a very deep well. The geometry of J-lay suits the geometry of the deep ocean. The Sapem 7000, one of the largest semi-submersible crane and pipelay vessels ever built, operates in exactly this mode for deepwater work. Its J-lay tower rises roughly 40 meters above the deck. Its total lifting capacity is 14,000 tons across its two cranes, a figure that exists almost outside intuition, but in pipelay mode, that engineering mass is focused on the precise, controlled vertical descent of pipe into water 2,000 or 3,000 meters deep. The vessel's semi-submersible hull suppresses wave motion, keeping the departure angle of the pipe stable even in significant sea states. Stability here is not comfort. It is a structural requirement. Every degree of uncontrolled vessel motion translates into a strain pulse that travels down the pipe. At depth, repeated strain pulses cause fatigue. Fatigue causes cracking. A crack in a deepwater gas pipeline, at 300 atmospheres of external pressure, is not a leak. It is a failure mode that propagates faster than any repair can reach it. This is the hidden engineering that surrounds every offshore gas flame, every heated home connected to a continental pipeline grid. Somewhere beneath the North Sea or the Gulf of Mexico or the waters off West Africa, there are steel tubes resting on the seabed that were lowered there joint by joint, each weld inspected by ultrasonic sensors before the next section was added, the entire catenary monitored in real time by engineers watching tension readouts and departure angle displays, all to keep a curve that no one will ever see within tolerances measured in fractions of a percent of yield stress. The S is not an accident of geometry. It is the only shape that satisfies every constraint simultaneously, the weight of the hanging pipe, the rigidity of the steel, the pressure of the deep ocean, and the physics of the catenary, all balanced on the tip of a tensioner setting that fits inside a window a few hundred tons wide. The next time you see a gas flame, you are seeing the far end of that calculation. We are surrounded by